Hi, my name is Min Chen. I'm Senior Staff Engineering from LinkedIn Service Infrastructure team.
Hi, I'm Karthik. I'm a Senior Staff Engineer from the Service Infrastructure team. Okay.
Today, Karthik and I will share how we enable GraphQL in linking to construct and query linking economic graph from our thousands existing RESTful service running in production. To adopt a type-safe query language like GraphQL, an important step is to build a data type system for the graph, namely GraphQL schema. Normally, this GraphQL schema is manually crafted. However, if your company already running microservice architecture, to rebuild this GraphQL schema from existing service definition and manually will be very costly and also easily go out of sync. And if you have an automatic tool to automatically generate the GraphQL schema from existing service definition will be very useful in this setting. Like any other companies, linking service infrastructure also goes through several phases of evolution. We starting with tightly coupled monolithic architecture and migrate to a microservice architecture to encourage decoupled developer experience. And up to now, we're providing a GraphQL federation access layer to support rich graph query. To address the pain point of complex orchestration and complex dependency from service exploration, and several years ago, LinkedIn adopted open source RESTful framework called RESTly to migrate away from the monolithic architecture to current microservice architecture. We have 10,000 RESTful service running in production to serve member data. And the Microsoft architecture provide very good developer experience with fine-grained service boundary. Although microservice architecture provide a good developer experience for API developer, client developer often run into a situation need to navigate linking economic graph to federate multiple REST service call to be able to present a view to our user. For such a scenario, it's very handy to have a GraphQL-like API to provide to a client developer. Then naturally a question coming up, can we layer GraphQL on existing microservice to provide a better user experience? The answer is yes. And the solution we proposed here is to through a declarative entity relationship-based service modeling. Next, I will hand over to Karthik to explain the detail of ER-based service modeling.
Thanks, Min. To adopt entity relationship using a declarative way of modeling on top of existing microservices, we followed the three strategies described here. The first was to continue using our existing microservice schema language to define the entities and continue developing the microservices in a distributed way. This was very important for LinkedIn because of our scale. Any solution that is not distributed is not going to scale at the level that LinkedIn is growing. And it is also important for us to keep our server developers happy who are familiar with our microservice framework and the way of building our services using them. The next strategy was to standardize how we model keys across all of LinkedIn. We wanted a way so that all the entities at LinkedIn use a standard way of defining all their keys, and these keys can be shared across all the microservices. And these keys will be used for all foreign key references in our entity schemas. For example, if you take a job posting entity as an entity and it needs to link to the company under which it's posted, that link will be defined by using a company key that is shared across LinkedIn. Next, finally, we extended the capabilities of our schema language to add support for adding relationships for related entities. The related entities can be thought of as a reverse relationship for a foreign key relationship. For example, like if you take the same example as the job posting linking to the company, a reverse relationship for that would be a list of jobs that are posted under the company. This is added on the company as a link to all the jobs for that company. To better understand how we went about adding this declarative ER modeling, we'll use an example scenario in this talk. In this example, we start with the bookstore on the left. A bookstore is a store that sells a collection of books, and a book can be sold by multiple bookstores. This is a many-to-many relationship, and normally we would model this relationship as a separate entity. But for this example, let's assume that the bookstore has an array of book key references. Then you have the book. A book can have one author. Like in this example, we just assume a book has a single author, and each author can have 0 or many books that they have written. And finally, on the right, you have the review entity, which describes a rating that was given to a book. Each review is associated with exactly one book, and a book can have 0 or more ratings. So with this example, these entities are going to be defined using our Pegasus schema language that's used by our microservice framework. And we then take these entities and build the microservices using them. So in the microservice world, in the microservices world, for each of these entities, you would have a separate collection, because LinkedIn is using the RESTful microservice architecture. We create a REST collection for each of the entities that we just saw. So we have 4 different collections, and each collection by default provides the GET API that returns back the entity that's represented by the key of that entity. In addition to these regular GET APIs, our microservices can also add additional Finder APIs, which allows you to search for a list of entities that match a particular criteria. Let's look at the examples that we have here. A bookstore has a Finder that allows you to look for all the stores that sells a particular book, and the criteria here is the book. Similarly, you have on the books, you can find all the books that are authored by a particular author, and the reviews, you have a Finder that returns all the reviews for a given book. So these finders actually model the reverse relationship I described earlier. And this is the state of the world at LinkedIn before we added AR modeling. Given that all these services are distributed and owned by different teams, they are going to be hosted in multiple microservices, and a client needs to orchestrate access across all of these microservices to get the data that they need. Now, in order to add declarative AR modeling on this set of microservices, the first thing we did was to standardize how we modeled keys in these microservices. So we required all the keys to be named types, and even for primitive keys, like integers or strings, we create something called a type ref that is supported by the Pegasus language, so that we could assign a name to that. And at LinkedIn, we have a central repository that holds the definition of all the keys that are used at LinkedIn. This creation of a central repository for all the keys was necessary even in the microservices world, because that allowed all these microservices to refer to other entities in the economic graph without directly creating a dependency on them. All you need to have to know is the key to those entities. Once you have all the key definitions, what we did for entity relationship was to add additional metadata on top of these keys. So we used the feature that Pegasus provides, which is a custom annotation, and we added this resource key annotation to indicate that this key can be resolved to fetch up an entity that it represents. In this example, we have a type ref book key, which represents a key to a book. And the resource key annotation explains that the resource or the microservice that we need to hit is the books collection. And it requires a key, and that key is basically the value of this the string key. And it also gives you a hint on what entity will be returned by that the microservice. The keys can also be complex types, and complex types are keys with multiple parts. We model them using records. This is a same example of a book key where it's a record. You can have multiple fields. In this example, we just have one field called book ID. These fields can then be referenced in the key config of the resource key annotation to build the URI that you can use to get that entity. So the infrastructure that's consuming this resource key annotation will be able to use both the details in the key and the annotation to get to build a REST API that will return back the entity represented by that key. Next, we look at how we added the capability of adding the reverse relationships. To do this, we created a Pegasus record called extensions for the entity that needs to be extended. And once you create this extension record, you can add all the related links as fields in the extension schema. So if you take a look at this example, we have a book and we want to include all the reviews of the book as an extension. So to do this, we create a book extension schema and add a field called reviews that links to an array of reviews. And this link is again defined using the review key, not the review entity directly. Once we have this, we added a couple of additional annotations to give additional metadata. In this case, the using extension.using provides the information of which finder API to call. Microservice can have multiple finders, and we need to know which finder to call. And the params config specifies all the parameters that needs to be filled by using fields of the entity that's being extended, in this case, the book. So the final REST finder API that gets constructed is like a request to the reviews microservice. This information again comes from the review key. And we are calling the find by book API by passing in the book entity's self-referencing book key as a parameter. Another example for extensions is the author extensions here. So the author extensions are very similar to the book extension, like we're extending the author entity to include books authored by an author. And this hits the books microservice and calls the find by author API and passes in the author's key as the parameter to search by. We made a conscious decision to co-locate the extension schema with the schema that's being extended. This allowed us to do validations at build time. For example, we can validate that all the extension fields are unique and they don't conflict with each other, and also that the extension fields that are getting added do not conflict with the fields in the author. This is very important to keep the distributed development of our microservices. So even at the build time, when the developers are writing these extension schemas, it is guaranteed that these relationships will be valid when we put them all together. So finally, this is what the entity's definitions look like after we add a declarative ER modeling. You have the original entities, but the extension schemas are added as highlighted in the blue here. All references are still using the key types, and with the additional information that all of the keys can have the metadata that the infrastructure can use to go and resolve the entity that it represents. Something to note here is that we added the extension relationships on the entity that was the source of the relation. For example, like the collection of reviews for a book is added in the book entity, not on the reviews entity. So this helps us, a client, to traverse this graph and go from one entity to all the related entities. For example, if somebody has a book key, they can resolve that book key to get the book it represents, and then follow the reviews link to get all the reviews for that book. Or if somebody has a book, they can use the author link to go to the author of that book, and then use the book's author link to get all the books that are authored by the same author of the original book. We still, even at this stage, all of this information is still distributed. The server developers are creating this in separate teams, and we need still to put them together to come as combined GraphQL schema. I'll hand it over to Min, who will talk about how we did that and what additional validations we did on top of the GraphQL schema.
Thank you, Karthik. So from the ER declarative modeling, we can build automatically generated two artifacts. The first one artifact is the GraphQL schema. This GraphQL schema, as demonstrated here, we take information from the ER service modeling. First, we replace the key reference to their entity they refer to. For example, here, original key field in author in the book is a foreign key. And in this case, in GraphQL schema, we replace to the author entity itself and put an annotation to say, is it derived? Next, we include a reverse relationship and represent from the extension schema Karthik just described. In this case, we include an additional field called reviews inside the book to list all the reviews written for this book. With both derived and extension schema, we can support the easy user query to from a book to find the detailed author information, and then from book to find all the reviews written for the book. And secondly, we also generate a letter JSON configuration file to capture the metadata information for the RESTful service at the runtime because they need to fetch from the RESTful service to get the real data. We call the REST resolver. And these two files create together to bring a link from a query, from GraphQL query to go to a RESTful service to fetch data from the microservice. There's a third issue we encountered when we built this automatic generation GraphQL schema is the data type system gap between our service entity schema definition and GraphQL type system. In the RESTful service infrastructure, REST we used, it used the Pegasus data language to describe the entity schema. And it has two important data types, but that's not covered in the GraphQL type system. One is called a map. For example, we showed here. In the bookstore, you can have a field to talk about the top selling books, which is a map from the book key, from the book name to the book key. And in the GraphQL type system, there's no map system, map data type. So to handle this gap, we convert a PDL map to a list of GraphQL object types. And in this graph object type, we call the data non-map entry here. It is actually an object type with only fixed field called a key and value. And the other type missing in the GraphQL type system is a union. Although GraphQL type have union to represent the different object type, but in the PDL, we have more complicated union scenario. The union can actually mix primitive type and the complex type together, which is not supported in the GraphQL. And for this, we convert our PDL union to a record where each union member, for example, the primitive complex memo here, will become an optional field for this object type. And to support our runtime system to know this is a translated type, we introduce a custom derivative called translated in the GraphQL type system, so that our GraphQL runtime engine can figure out when to do the data translation to get back data from microservice and to comply with GraphQL type system. So it is very important to note that service and the clients can upgrade very separately. So it's very important to notify developers of their change made in the service will not cause backward incompatible change to the GraphQL schema or break all the existing GraphQL query. And at the linking scale, we prefer to do the schema validation as early as possible at the development cycle. So in this case, when people check in the service change, we would like to validate their schema change to notify them and then give them build error to tell them they cannot make this change because this may break their GraphQL schema later on in stitch. So we would like to provide the wording as early as possible so that we can later on, when we stitch the GraphQL schema, we can ensure the schema is always valid and backward compatible. Corresponding to three pillars Karthik just mentioned for our ER service modeling, we can build a backward compatibility checker to guard those three types of incompatibility changes API developer may make. So first, we can guard incompatible in entity definition change evolution. Secondly, we can guard incompatible key definition evolution. Lastly, we can also guard incompatible extension schema definitions. The way we build this backward compatibility checker is to build a snapshot version from the ER modeling. At the service build time, we will compare the new service modeling with the snapshot we kept and detect potential backward incompatible, and then prevent service developer to commit their changes. Here can give you 3 concrete examples what is backward incompatible change that the developers normally make. So the first example, developer changed the data type from entity schema definition from int to flow, which this is definitely incompatible. The second one, developer may change the key reference from original book to the later on book v2 for the same foreign key. That will cause the GraphQL schema resolve to a different object type than the original GraphQL query were broken. The third type, people may change extension field to change the previous reverse relationship reviews from list of review to a list of author. This is also backward incompatible because federated GraphQL schema later on, this extension field data type will change. Then the query also will broken. So with this early warning to the developer in the distributed environment system is very helpful to avoid such backward incompatible change that will impact client user experience. So to sum up, here, let's go over what is overall GraphQL workflow we proposed here with ER-based service model in the picture. We start with entity relationship model definition, which include both entity schema definition and extension schema to describe reverse relationship. And we built a GraphQL schema generator, which produced 2 major artifacts, GraphQL schema and the REST resolver config. And this all done at build time. Then at the runtime, GraphQL schema and REST resolver will be the input for us to instantiate our GraphQL engine. And the GraphQL engine on receive a GraphQL query, they will use this metadata information to config microservice data loader to fetch data from our microservices. And then apply data translator to translate the data from the microservice to comply with GraphQL schema we generate. Finally, we can return the GraphQL response to the user. This is all in our runtime flow. Thank you, everybody, to join our talk, and feel free to connect us on the LinkedIn. Thanks.
Thank you.